So it's on integrated silicon photonics platforms for scalable quantum systems. That's a joint invention between the UNM and the University of Rochester. My co-inventors are Ganesh Balakrishnan, who is working just like I do at the Center for High Technology Materials, so CHTM, and Arash Mafi, who is also working at CHTM, and then Roman Sobolewski, who is at the University of Rochester. This particular invention is directly arising from the NSF project that is listed on the slide. We received around $750,000 from NSF to work on this project. We are now in the early stages of the third year. We might end up doing no cost extension due to COVID, but that remains to be seen. So some background about the quantum information science. Well, it's a field that rarely you're able to participate in such an opportunity when we are at the stage of going from many years of purely physics laboratory experiments to actual industrial applications where the field moves very fast from physics to engineering. And that creates a huge opportunity for investors. I think I can compare that to, early days of Microsoft, for example, or early days of Apple. Those who invested at the time are probably very happy now. So what triggered the strong interest in the US in this field is illustrated in that right top corner. And that was a demonstration in 2017, in June of 2017, of long distance quantum communication by China over more than 1,200 kilometers, when the previous record was maybe about 80 kilometers. So that kind of woke up many politicians in the US and the military too, to the fact that China actually took the leadership in this field. And that creates a lot of potential threats. Therefore, a year later, in December of 2018, Congress has approved or has voted on the National Quantum Initiative Act, and it was signed by President Trump in December of 2018, with the goal of providing a coordinated federal program that would, sorry, my slides are not reacting. I don't know what happened, but my computer is not behaving. Now it says it's sticky. Okay, now it's behaving again. Okay, so it provides funding for new programs at the federal level that would accelerate quantum research and development at NSF, at Department of Energy, at Department of Defense, to basically bring US to par with the progress elsewhere, especially in China. So what is quantum information processing? In the context of this particular invention, we focus on photonics, but this is not the only vehicle that could be used for quantum information processing. There are many others as well. So in general, it relies on the extraction, processing, and manipulation, as well as transmission and detection of information by making use of quantum properties of light and matter. That's very generic definition. And in terms of applications, and that is not necessarily a complete list, but this is what currently people focus on, is on one hand, secure communication, cryptography, quantum cryptography, ultra-precise sensors, and then quantum computing, which is expected to extend our ability to compute problems that are not possible to handle by the current computers. Examples of those problems are large-scale molecular simulations for material design, drug discovery, and then connecting networks using the quantum communications, either of sensors or other distributed computers. And it may have many applications, including biological imaging, gravitometry, and position, navigation, timing. So there has been a group of pioneering companies which are shown on this slide. These are the US-based companies. The biggest players are IBM, Google, Microsoft, and Intel, but there are many also much smaller ones, and there will be many, many more. In fact, I could not include it here, but I have a list of just quantum computing companies in the world, and it's already like 100 of them. At the bottom, you see other countries that also are leaders in this field. I mentioned China, but aside from China, Australia is very strong, UK, Japan, European Union in general, and Singapore. So until now, I mentioned most of the work has been done in the labs. And in terms of photonics, it was components, large bulk components on optical tables. There has been a lot of progress using that approach, but it's not something that can be easily transferred to industry. Most recently, the emphasis is on integration of various components into scalable systems compatible, let's say, with the silicon manufacturing industry. So on the right-hand side, you see a couple of illustrations. The top one is the superconducting nanowire detector that would communicate with outside environment by, first of all, getting the light coupled to it from an external source, and then the output would be collected electrically. Below, there is a standard single-photon detection experiment, which would have, again, a large pump laser, another single-photon source, combined in the bulk up-conversion crystal, and then you would have a beam splitter, and you would have two detectors and electronics. So all that takes a big space on the optical table. Our approach is to meet the challenge of integrating the basic components of the quantum information processing systems on a single silicon chip. So that way, it will be possible to scale the applications to perform functions that currently, as I said, are not even possible. Earlier this year, Google has demonstrated maybe some 56 qubits of superconducting elements that performed computation faster than any classical computer would. But these are still very, very early stages. And again, this is not what is scalable at this stage. Our approach is to use silicon-based devices as the silicon technology is inexpensive and very suitable for applications in quantum computing. So here is an illustration of the concept where on the left-hand side, you see a couple of waveguides that on one side have an emitter, single photon emitter or entangled photon pair emitter. On the opposite end, there is a detector. And on the right-hand side, the figure shows a cross-section of those two waveguides. There are silicon dioxide cladding, silicon nitride core, and then in the middle of each of those waveguides, you have an emitter, which is coupled to those waveguides directly on the chip. And it's a single quantum dot emitter that, depending on the configuration, can either emit individual photons or it can emit photon pairs, entangled photon pairs. That's basically the goal of the current NSF supported project that we have, is to demonstrate the first integrated system where the source, waveguide, and detector would be all on a single chip. And at the bottom, the illustration of those two figures is the distinction between a single photon emitter and entangled photon pair emitter. Otherwise, those figures look very similar. The only difference is that for the entangled photon pair, we would have the niobium nitride electrode coming very, very close to the quantum dot. So it'd be possible to directly inject Cooper pairs of electrons and holes into the active region of the quantum dot. If they are further away, if the electrode is too far, then those Cooper pairs would dissociate and you would have single electron or single hole ejection. This is an illustration of our work on the nanowire superconducting single photon detector. That work was presented in September in the Quantum 2.0 conference organized by the Optical Society of America. And it contains an option for the light coming in the waveguide. Then it's split into two separate arms. One goes outside for another single photon detector outside to basically characterize our device by comparing that with readings from the other detector. And our device is shown in this part here. It has a U-shaped, elongated superconducting nanowire directly on top of the waveguide core. So when the photon is absorbed by that nanowire, it creates a local hotspot, which raises the temperature above the critical temperature for superconductivity, and suddenly the resistance of that nanowire gets bigger, and that way you can detect the presence of the detector. And then on the right-hand side, what you see on top is our design for placing our chip, which is in the middle, onto a submount, which then goes directly into our 4 Kelvin cryostat and can couple photons in and out by those two vertical magenta fibers. Now, we were originally planning to have that done earlier this year, but because of coronavirus, I'm closed in March for any students. So the work is a little bit delayed, but we hope to start first testing of those fabricated circuits in December. Now, in terms of the market, as I said, this is a golden opportunity because very rarely we have a situation when something very big, which is estimated within less than 10 years to reach multiple billions in each of those possible application fields, whether it's quantum cryptography or sensing or networking or computing. Each of those are multi-billion markets predicted within 5 to 9 years from now. And there's an enormous potential for investing in small companies, such as might be created to commercialize our technology, which then might either grow bigger themselves or be purchased by those giants like Google or Microsoft, who will be definitely be acquiring technology that way as well. So this is the end of my presentation.
Great. Well, thank you, Marek. Thank you for providing insight into the quantum computing market on this slide. So one question is, what commercial path forward do you see for this invention? That is to say, do you imagine that specific companies will see this as a fit into their current quantum technologies, or is this more of a fit into its own startup company that could eventually be incorporated into existing technologies?
Of course, we are open, and we should be open to many different avenues, but what seems to me most likely is that some of our more entrepreneurial students who are working on the project might be interested in setting up a company, because then they will know all the technology, will have access to all the technology required to make those devices, and then they can continue that work towards actually commercialization.
Great. I think that's all the questions we have. And if you guys do have any other questions, feel free to shoot either myself or Greg emails, and we can also get those answered afterwards. But thank you, Marek, for your presentation.